All right. Pull that down a little bit. That should be all right. I don't have to focus too hard. Get a drinky winky. Oh, yeah. Oh, shoot. This is going to be hard. So, I took another little nap and I connected to the cycler for the night. But, oh my gosh. It is just hard to get myself back up. I think it's just because I'm working more, not resting as much as I'm accustomed to. So, just going to take some time to adapt. Got to push through it. So, gonna try. Chemistry 2E. I can't wait to do some of these problems. Ooh, thermochemistry. Thermochemistry is fun. That's where all the fun experiments. A lot of the fun experiments are. Come on. Ah. So I'm stuck. I connect to a device that does some blood filtering for me every night, and so I'm basically on a little extension cord. That's as far as I can go. I go like 12 feet, I think, from the machine. I can disconnect whenever I want to, but it's a process doing that. It's much easier just to stay connected. So hold on. I just didn't realize how loud that was. There we go. Let's get some. Let's get some rain. Heavy rainstorm. There you go. God, I hate those ads so much. It's like a character. It's like an isometric view, and he's got a level above his head, and he has to go around like attacking enemies and picking up equipment and stuff. They're so dumb. It's like they purposely fail the missions in order to get you enticed into playing it, but um, yeah, thermochemistry is cool. You get to heat stuff up and you get to sometimes blow stuff up in a controlled way. Bomb calorimetry comes to mind. I did that my senior year in college for physical chemistry. I think it was C6 compounds, hexane, hexine. No, hexine doesn't exist. No, hexine. No, it was cyclohexane, cyclohexene, dicyclohexene, and then um, benzene. Because benzene's interesting. And you get that third delocalized. Well, I guess I would say delocalized. When you get that third set of electrons involved with that benzene, it orients the molecule in a different way. It's interesting. It's cool. But yeah, so I'm going to talk about some chemistry. We're going to do chapter 5. Got to finish that here. I'd like to finish it. I was thinking next week would be a nice time to finish it. Maybe next weekend. Thought I said Wednesday, not last time, but I'm always changing my mind. So I don't have strict deadlines because I don't think I'm going to die. Like, that's basically the intent of a deadline, is to simulate the feeling that someone's going to die if something doesn't get done. And sometimes that happens, yeah. Like, if my people didn't send me dialysis supplies every month, then yeah. But anywho, I'm feeling a lot more pumped up now. I have this weird thing, like, I haven't noticed this before. I was thinking, I kept thinking it was sleep, but my sleep apnea was coming back. But it almost feels like it's like, because my mind, I know I don't want to get or go to bed right now. So I'm trying not to fall asleep. But when I have my eyes closed long enough, I just feel like I start to shut down. It's like I can't help it. So, all right, well, that's enough rambling. OpenStax Chemistry, Chapter 5, while listening to and watching, I guess, a very intense rainstorm that's like blowing sideways. Okay. All right. Chapter 5, Chapter Outline. 1. Energy Basics. 2. Calorimetry. 3. Enthalpy. Introduction. Chemical reactions such as those that occur when you light a match involve changes in energy as well as matter. Societies at all levels of development could not function without energy released by chemical reactions. In 2012, about 85% of U.S. energy consumption came from the combustion of petroleum products, coal, wood, and garbage. We use this energy to produce electricity, to transport food, raw materials, manufactured goods and people, for industrial production, and to heat and power our homes and businesses. While these combustion reactions help us meet essential energy needs, they are also recognized by the majority of the scientific community as a major contributor to global climate change. Useful forms of energy are also available from a variety of chemical reactions other than combustion. For example, the energy produced by the batteries in a cell phone, car, or flashlight results from chemical reactions. This chapter introduces many of the basic ideas necessary to explore the relationships between chemical changes and energy, with a focus on thermal energy. 1. Energy basics. At the end of this section, you'll be able to define energy, distinguish types of energy, and describe the nature of energy changes that accompany chemical and physical changes, distinguish the related properties of heat, thermal energy, and temperature, define and distinguish specific heat and heat capacity, and describe the physical implications of both, perform calculations involving heat, specific heat, and temperature change. Chemical changes and their accompanying changes in energy are important parts of our everyday world. The macronutrients in food, proteins, fats, and carbohydrates undergo metabolic reactions that provide the energy to keep our bodies functioning. We burn a variety of fuels, gasoline, natural gas, and coal to produce energy for transportation. Sorry. Every once in a while, I get these really, really sharp pains in my leg, like little localized pains. Oh, yeah. That freaking hurt. Ah, dang it. Mm, mm. Oh, gosh. So what do? I squeeze it. Because that does, that tells my body to produce some stuff to help address the pain. Whoa, that hurt, though. So we burn a variety of fuels, gasoline, natural gas, and coal, to produce energy for transportation, heating, and the generation of electricity. Industrial chemical reactions use enormous amounts of energy to produce raw materials such as iron and aluminum. Energy is then used to manufacture those raw materials into useful products such as cars, skyscrapers, and bridges. Over 90% of the energy we use comes originally from the sun. Every day, the sun provides the Earth with almost 10,000 times the amount of energy necessary to meet all the world's energy needs for that day. Our challenge is to find ways to convert and store incoming solar energy so that it can be used in reactions or chemical processes that are both convenient and non-polluting. Plants and many bacteria capture solar energy through photosynthesis. We release the energy stored in plants when we burn wood or plant products such as ethanol. We also get this energy to fuel our bodies by eating food that comes directly from plants or from animals that got their energy by eating plants. Burning coal and petroleum also releases stored solar energy. These fuels are fossilized plant and animal matter. The chapter will introduce the basic ideas of the important area of science concerned with the amount of heat absorbed or released during chemical and physical changes, an area called thermochemistry. The concepts introduced in this chapter are widely used in almost all scientific and technical fields. Food scientists use them to determine the energy contents of foods. Biologists study the energetics of living organisms, such as the metabolic combustion of sugar into carbon dioxide and water. The oil, gas, and transportation industries, renewable energy providers, and many others endeavor to find better methods to produce energy for our commercial and personal needs. Engineers strive to improve energy efficiency, find better ways to heat and cool our homes, refrigerate our food and drinks, and meet the energy and cooling needs of computers and electronics. Among other applications, understanding thermochemical principles is essential for chemists, physicists, biologists, geologists, every type of engineer, and just about anyone who studies or does any kind of science. Oh, energy. Energy can be defined as the capacity to supply heat or to do work. One type of work is the process of causing matter to move against an opposite force. For example, we do work when we inflate a bicycle tire. We move air, the air in the pump, against the opposing force of the air already in the tire. Like matter, energy comes in different types. One scheme classifies energy into two types: potential energy and the energy an object has because of its relative position, composition, or condition, and kinetic energy, the energy that an object possesses because of its motion. Water at the top of a waterfall or a dam has potential energy because of its position. When it flows downward through the generators, it has kinetic energy that can be used to do work and produce electricity in a hydroelectric plant. A battery has a potential because the chemicals within it can produce electricity that can do work. Energy can be converted from one form into another, but all of the energy present before a change occurs always exists in some form after the change is completed. This observation is expressed in the law of conservation of energy. During a chemical or physical change, energy can be neither created nor destroyed, although it can be changed in form. This is also one version of the first law of thermodynamics, as you will learn later. When one substance is converted into another, there is always an associated conversation of one form of energy into another. Sorry, conversion. Um, Heat is usually released or absorbed, but sometimes the conversion involves light, electrical energy, or some other form of energy. For example, chemical energy, a type of potential energy, is stored in the molecules that compose gasoline. When gasoline is combusted within the cylinders of a car's engine, uh, the rapidly expanding gaseous products of this chemical reaction generate mechanical energy, a type of kinetic energy, when they move the cylinder's pistons. According to the law of conservation of matter, seen in an earlier chapter, there is no detectable change in the total amount of matter during a chemical change. When chemical reactions occur, the energy changes are relatively modest, and the mass changes are too small to measure, so the laws of conservation of matter and energy hold as well. However, in nuclear reactions, the energy changes are much larger, by factors of a million or so. The mass changes are measurable, and matter energy conversions are significant. This will be examined in more detail in a later chapter on nuclear chemistry. Ah, God, that hurts. Shoot. Sorry, just touching it just causes my whole body to jump in pain. I'm going to pause for a minute. All right, I put my sweatpants on, so hopefully it doesn't hurt as much when I touch it through the sweat. Oh my gosh, whoa. It's been a long time since I've had those, though. That's annoying. I was getting those, I think, if I remember right, I was getting those a lot in Nebraska right before I left here. But all right. Thermal energy, temperature, and heat. Thermal energy is kinetic energy associated with the random motion of atoms and molecules. Temperature is a quantitative measure of hot or cold. When the atoms and molecules in an object are moving or vibrating quickly, they have a higher average kinetic energy, and we say that the object is hot. When the atoms and molecules are moving slowly, they have lower average kinetic energy, and we say that the object is cold. Mm. Sorry, I just realized my glasses aren't on me. Um, oh, no. Yeah, right there. Okay, cool. Uh, Assuming that no chemical reaction or phase change, such as melting or vaporizing, occurs, increasing the amount of thermal energy in a sample of matter will cause its temperature to increase. And assuming that no chemical reaction or phase change, sorry, should take me a second to get back into it. Phase change, assuming no chemical reaction, such as condensation or freezing occurs, decreasing the amount of thermal energy in a sample of matter will cause its temperature to decrease. Most substances expand as their temperature increases and contract as their temperature decreases. This property can be used to measure temperature changes, as shown in the figure. The operation of many thermometers depends on the expansion and contraction of substances in response to the temperature changes. Hold on one second. I'm going to pause again. Okay, that should do it. Sorry. Uh, the operation of many thermometers depends on these temperature changes. Okay. Heat is the transfer of thermal energy between two bodies at different temperatures. Heat flow, a redundant term but one commonly used, increases the thermal energy of one body and decreases the thermal energy of the other. Suppose we initially have a high temperature and high thermal energy substance and a low temperature and low thermal energy substance. The atoms and molecules in the high one have a higher average kinetic energy than those of the low one. If we place the high substance in contact with the low substance, the thermal energy will flow spontaneously from the high substance to the low substance. The temperature of the high substance will decrease, and as will the average kinetic energy of its molecules. The temperature of the low substance will increase, along with the average kinetic energy of its molecules. Heat flow will continue until the two substances are at the same temperature. Okay. Matter undergoing chemical reactions and physical changes can release or absorb heat. A change that releases heat is called an exothermic process. For example, a combustion reaction that occurs when using an oxyacetylene torch is an exothermic process. This process also releases energy in the form of light, as evidenced by the torch's flame. A reaction or change that absorbs heat is an endothermic process. A cold pack used to treat muscle strains provides an example of an endothermic process. When the substances in the cold pack, water and salt like ammonium nitrate, are brought together, the resulting process absorbs heat, leading to the sensation of cold. Historically, energy was measured in units of calories. A calorie is the amount of energy required to raise 1 gram of water by 1 degree Celsius. However, this quantity depends on the atmospheric pressure and the starting temperature of the water. The ease of measurement of energy changes in calories has meant that the calorie is still frequently used. The calorie, with the capital C, or large calorie, commonly used in quantifying food energy content, is a kilocalorie. The SI unit of heat, work, and energy is the joule. A joule is defined as the amount of energy when a force of 1 Newton moves an object 1 meter. It is named in honor of the English physicist James Prescott Joule. 1 joule is equivalent to 1 kilogram meter squared per second squared, which is also called 1 Newton meter. A kilojoule is 1,000 joules. To standardize its definition, 1 calorie has been set equal to 4.184 joules. We now know or introduce 2 concepts useful in describing heat flow and temperature change. The heat capacity of a body of matter is the quantity of heat it absorbs or releases when it experiences a temperature change of 1 degree Celsius. So C equals Q over delta T. Heat capacity is determined by both the type and amount of substance that absorbs or releases heat. It is therefore an extensive property. Its value is proportional to the amount of the substance. For example, consider the heat capacities of 2 cast iron frying pans. The heat capacity of the large pan is 5 times greater than that of the small pan because, although both are made of the same material, the mass of the large pan is 5 times greater than the mass of the small pan. More mass means more atoms are present in the larger pan, so it takes more energy to make all those atoms vibrate faster. The heat capacity of the small cast iron frying pan is found by observing that it takes 18,150 joules of energy to raise the temperature of the pan by 50 degrees Celsius. So, oh my gosh, I had never made that connection. Obviously, it is the same fucking thing. Sorry, pardon my language, but oh my god. 6 years of chemistry, and I never once thought of a calorimeter or thought of a frying pan as a freaking calorimeter. That's hilarious. Oh, what the heck? That's just so annoying. I mean, it's funny. It's still good that I know it now, but it's so freaking obvious. Because what is a calorimeter? A calorimeter setup is designed to measure the heat of materials and stuff. It's supposed to help insulate that heat, some of that heat energy, so it doesn't go to the environment. And you can usually measure the temperature of that. That's too funny. So the heat capacity of the small pan equals 18,140 joules over 50 degrees Celsius. And so the heat capacity is 363 joules per degree Celsius, assuming it's a linear process. The larger cast iron frying pan, while made of the same substance, requires 90,700 joules of energy to raise its temperature by 50 degrees Celsius. The larger pan has a proportionally larger heat capacity because the larger amount of material requires a proportionally larger amount of energy to yield the same temperature change. So the heat capacity of a large pan, when the equations are thrown in, it's 1,814 joules per degree Celsius. So what is that? Almost 6 times higher, 5 to 6 times higher than the small pan. So that means in order to change by the same temperature, you need almost 6 times more energy to heat the larger pan to the same degree. That's crazy. The specific heat capacity of a substance, commonly called its specific heat, is the quantity of heat required to raise the temperature of 1 gram of substance by 1 degree Celsius. Oh, never mind. That one of the first things that I was saying before, I meant it for this equation, I think, because this is in terms of 1 degree. This is going to create like a slope on a graph. So little c equals q over q over m delta t. So q, heat, m is mass, delta t is the change in temperature. Specific heat capacity depends only on the kind of substance absorbing the heat or releasing heat. It is an intensive property, the type, but not the amount of the substance is all that matters. For example, the small cast iron frying pan has a mass of 808 grams. The specific heat of iron, the material used to make the pan, is therefore, and then you get 0.449 joules per gram degree Celsius. The large frying pan has a mass of 4,040 grams, blah, 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 0.449 joules per gram degree Celsius. Oh, wow. It's the same. It's because the material used is the same, but because you used more of it in one case than the other, it's going to take more energy to heat up more atoms. But each of those atoms is still constant at that same 4.449. Although the large pan is more massive than the small pan, since both are made of the same material, they both yield the same value for specific heat for the material of construction, iron. Note that specific heat is measured in units of energy per temperature per mass and is an intensive property, being derived from a ratio of two extensive properties, heat and mass. The molar heat capacity, also an intensive property, is the heat capacity per mole of a particular substance and has units of joules per mole degree Celsius. Water has a relatively high specific heat, about 4.2 joules per gram degree Celsius for a liquid, 2.09 for the solid. Most metals have much lower specific heats, usually less than 1 joule per gram degree Celsius. The specific heat of a substance varies somewhat with the temperature. However, this variation usually small enough that we will treat specific heat as constant over the range of temperatures that will be considered in this chapter. Specific heats of some common substances are listed in Table 5.1. If we know the mass of a substance and its specific heat, we can determine the amount of heat, Q, entering or leaving the substance by measuring the temperature change before and after the heat is gained or lost. So Q equals specific heat times mass of substance times temperature change. Q equals little c m delta t, which equals Cm times T final minus T initial. In this equation, C is the specific heat of the substance, M is its mass, and delta T, which is red, delta T, is the temperature change, T final minus T initial. If a substance gains thermal energy, its temperature increases, its final temperature is higher than its initial temperature, final minus initial, has a positive value, and the value of Q is positive. If a substance loses thermal energy, its temperature decreases. The final temperature is lower than the initial temperature. T final minus T initial has a negative value, and the value of Q is negative. Note that the relationship between heat, specific heat, mass, and temperature change can be used to determine any of these quantities, not just heat, if the other three are known or can be deduced. (5.2) Calorimetry. By the end of this section, you'll be able to explain the technique of calorimetry, calculate and interpret heat and related properties using typical calorimetry data. One technique we can use to measure the amount of heat involved in a chemical or physical process is known as calorimetry. Calorimetry is used to measure amounts of heat transferred to or from a substance. To do so, the heat is exchanged with a calibrated object, calorimeter. The temperature change measured by the calorimeter is used to derive the amount of heat transferred by the process under study. The measurement of heat transfer using this approach requires the definition of a system, the substance or substances undergoing the chemical or physical change, and its surroundings. All other matter, including components of the measurement apparatus that serve to either provide heat to the system or absorb heat from the system. A calorimeter is a device used to measure the amount of heat involved in a chemical or physical process. For example, when an exothermic reaction occurs in a solution in a calorimeter, the heat produced by the reaction is absorbed by the solution, which increases its temperature. When an endothermic reaction occurs, The heat required is absorbed from the thermal energy of the solution, which decreases its temperature. The temperature change, along with the specific heat and mass of the solution, can then be used to calculate the amount of heat involved in either case. Calorimetry measurements are important in understanding the heat transferred in reactions involving everything from microscopic proteins to massive machines. During her time at the National Bureau of Standards, research chemist Reatha Clark King performed calorimetric experiments to understand the precise heats of various fluorine compounds. Her work was important to NASA in their quest for better rocket fuels. Scientists use well-insulated calorimeters that all but prevents the transfer of heat between the calorimeter and its environment, which effectively limits the surroundings to the non-system components with the calorimeter and the calorimeter itself. This enables the accurate determination of the heat involved in chemical processes. The energy content of foods, and so on. General chemistry students often use simple calorimeters constructed from polystyrene cups. These easy-to-use coffee cup calorimeters allow more heat exchange with the outside environment and therefore produce less accurate energy values. Commercial solution calorimeters are also available. Relatively inexpensive calorimeters often consist of two thin-walled cups that are nested in a way that minimizes thermal contact during use, along with an insulated cover, handheld stirrer, and simple thermometer. More expensive calorimeters used for industry and research typically have a well-insulated, fully enclosed reaction vessel, motorized stirring mechanism, and a more accurate temperature sensor. Before discussing the calorimetry of chemical reactions, consider a simpler example that illustrates the core idea behind calorimetry. Suppose we initially have a high-temperature substance, such as a hot piece of metal, and a low-temperature substance, such as cool water. If we place the metal in the water, heat will flow from M to W. The temperature of M will decrease, and the temperature of W will increase until the two substances have the same temperature. That is, when they reach thermal equilibrium. If this occurs in a calorimeter, ideally all of this heat transfer occurs between the two substances with no heat gained or lost by either its external environment. Under these ideal circumstances, the net heat change is zero. Q substance plus metal plus Q substance water equals zero. This relationship can be rearranged to show the heat gained by substance metal is equal to the heat lost by substance water. Magnitude of the heat change is therefore the same for both substances, and the negative sign merely shows that the heat from one and the heat from the other are opposite in direction of heat flow, gain or loss, but does not indicate the arithmetic sign of either Q value. That is described by whether the matter is in question gains or loses heat, per definition. In the specific situation described, the heat of the substance metal is a negative value and heat of the water is positive, since heat transferred from metal to the water. Ouch. When we use calorimetry to determine the heat involved in a chemical reaction, the same principles we have been discussing apply. The amount of heat absorbed by the calorimeter is often small enough that we can neglect it, though not for highly accurate measurements as discussed later. And the calorimeter minimizes energy exchange with the outside environment. Because energy is neither created nor destroyed during a chemical reaction, the heat produced or consumed in the reaction, the system, Q reaction, plus the heat absorbed or lost by the solution, the surroundings, Q solution, must add up to zero. This means that the amount of heat produced or consumed in the reaction equals the amount of heat absorbed or lost by the solution. This concept lies at the heart of all calorimetry problems and calculations. If the amount of heat absorbed by a calorimeter is too large to neglect, or if we require more accurate results, then we must take into account the heat absorbed both by the solution and the calorimeter. The calorimeters described are designed to operate at constant atmospheric pressure and are convenient to measure heat flow accompanying processes that occur in solution. A different type of calorimeter that operates at constant volume, colloquially known as a bomb calorimeter, is used to measure the energy produced by reactions that yield large amounts of heat and gaseous products, such as combustion reactions. The term bomb comes from the observation that these reactions can be vigorous enough to resemble explosions that would damage other calorimeters. This type of calorimeter consists of a robust steel container, the bomb, which contains the reactants and is itself submerged in water. The sample is placed in the bomb, which is then filled with oxygen at high pressure. A small electrical spark is used to ignite the sample. The energy produced by the reaction is absorbed by the steel bomb and the surrounding water. The temperature increase is measured and, along with the known heat capacity of the calorimeter, is used to calculate the energy produced by the reaction. Bomb calorimeters require calibration to determine the heat capacity of the calorimeter and ensure accurate results. The calibration is accomplished using a reaction with a known heat, such as a measured quantity of benzoic acid ignited by a spark from a nickel fused wire that is weighed before and after the reaction. The temperature change produced by the known reaction is used to determine the heat capacity of the calorimeter. Calibration is generally performed each time before the calorimeter is used to gather research data. Yep, I used one of those. It's pretty cool. It's the bomb. I'm so excited to talk about instrumentation later on. I used to hate that class. It used to be so boring. But now that I understand like the process in making those things and how like they can be used to measure certain properties, like it's wicked. Since the first one was constructed in 1899, 35 calorimeters have been built to measure the heat produced by a living person. These whole-body calorimeters of various designs are large enough to hold an individual human being. More recently, whole-room calorimeters allow for relatively normal activities to be performed. And these calorimeters generate data that more closely reflect the real world. These calorimeters are used to measure the metabolism of individuals under different environmental conditions, different dietary regimes, and with different health conditions such as diabetes. For example, Carla Prato's team at University of Alberta undertook whole-body calorimetry to understand the energy expenditures of women who had recently given birth. Studies like this help develop better recommendations and regimens for nutrition, exercise, and general well-being. During this period, a significant physiological change in humans' metabolism is typically measured in calories per day. A nutritional calorie is the energy unit used to quantify the amount of energy derived from the metabolism of foods. 1 calorie is equal to 1,000 calories, the amount of energy needed to heat 1 kilogram of water by 1 degree Celsius. 3. Enthalpy. By the end of this section, you'll be able to state the first law of thermodynamics, define enthalpy, and explain its classification as a state function, write and balance thermochemical equations, calculate enthalpy changes for various chemical reactions, explain Hess's law, and use it to compute reaction enthalpies. Oh, I just thought of the coolest idea. So the old scrolls for like literary works and for things like the Bible or like the prophecies in the Bible and stuff, they were in these massive, massive scrolls. Basically one long sheet of paper. And I just remembered that the schools had those big rolls. I have to look this up right now. I have to. This is like, this should be so fun. Do like a scroll of chemistry. Just like record myself doing it. Oh, dude, that'd be so fun. And maybe like paint it or something. Oh, dude, that'd be so badass. Oh, dude, that is so cool. Um, Paper scroll. Let's just look at this. Let's see what they got. No. How about massive paper roll? Actually, let's do this. Let's go. Let's ask AI for this one. Open AI, Chat GPT. Daily logbook. I need to start doing that in the morning before I leave. Okay. Where can I buy those massive paper rolls that are used in school classrooms? They come in various colors, but I don't know the technical term for it. Bulletin board, butcher paper. Bitch, butcher paper. That's right. Butcher paper. Oh my gosh. Dude, that is going to be so fun. Oh yeah, that's literally what like oh my gosh, that is freaking what VHS. A VHS is a freaking scroll. That's crazy. That's so cool. I'm so sorry. I don't usually get excited over silly things like this, but it's just so funny seeing the similarities. Because the VHS, the medium of the VHS is the negative, and the negative comes in a roll. But the roll isn't like equal. Yeah, the roll you just pull it out, pulls out, and then rolls back up into the other side. That is so freaking ridiculous. That makes for a really fun project, though. For if I read a book, I can translate it to a freaking scroll using yeah. If I use a paintbrush, that's like art, dude. That is so crazy. Or maybe what I can do is instead of word for word, because that would take forever, and most of a textbook is filler anyways. I just get the basic ideas, summarize the whole book into digital, and then once I have it in a digital form, I can just translate it straight onto the paper. Okay, yeah, no, that'll be my first little like final project. That'll be like I did it. I understand what I read in this book. That's so cool. All right, Amazon butcher paper. Roll. Sorry. 100 feet. Okay. Sorry. That totally got me distracted. That just got me so excited. So the issue I've had is like, how do I keep myself convinced I need to keep doing this? Because I want to do this, because I want to teach. But the problem is I don't want it to just be technical stuff. I want it to be something that I just, uh, something that's like a lifestyle. But lifestyles have to be fun in addition to just getting the things done. So, all right, sorry. Okay, let's reread. State the first law of thermodynamics. Write enthalpy and explain its classification as a state function. Write and balance thermochemical equations. Calculate enthalpy changes for various chemical reactions. Explain Hess's law and use it to compute reaction enthalpies. Thermochemistry is a branch of chemical thermodynamics, the science that deals with the relationships between heat, work, and other forms of energy in the context of chemical and physical processes. As we concentrate on thermochemistry in this chapter, we need to consider some widely used concepts of thermodynamics. Substances act as reservoirs of energy, meaning that energy can be added to them or removed from them. Energy is stored in a substance when the kinetic energy of its atoms or molecules is raised. The greater kinetic energy may be in the form of increased translations, travel or straight line motions, vibrations or rotations. The atoms or molecules, when thermal energy is lost, the intensities of these motions decrease and the kinetic energy falls. The total of all possible kinds of energy present in a substance called the internal energy, sometimes symbolized as E. As a system undergoes a change, its internal energy. Sorry, I had to make sure the microphone was on. So I actually was reading, and that would have been funny if it wasn't, because then that would have been 2 hours that I didn't record. Change. Energy can be transferred from the system to the surroundings or from surroundings to the system. Energy is transferred into a system when it absorbs heat from the surroundings or when the surroundings do work on the system. For example, energy is transferred into a room temperature metal wire if it is immersed in hot water. The wire absorbs heat from the water, or if you rapidly bend the wire back and forth, the wire becomes warmer because of the work done on it. Both processes increase the internal energy of the wire, which is reflected in an increase in the wire's temperature. Conversely, Energy is transferred out of a system when heat is lost from the system or when the system does work on the surroundings. The relationship between internal energy, heat, and work can be represented by the equation delta U equals Q plus W, as shown in figure 519. This is one version of the first law of thermodynamics, and it shows that internal energy of the system changes through heat flow into or out of the system. Positive Q is heat flow in, negative Q is heat flow out, or work done on or by the system. The work W is positive if it is done on the system, and negative if it is done by the system. A type of work called expansion work, or pressure volume work, occurs when a system pushes back the surroundings against a restraining pressure, or when the surroundings compress the system. An example of this occurs during the operation of an internal combustion engine. The reaction of gasoline and oxygen is exothermic. Some of this energy is given off as heat, and some does work pushing the piston in the cylinder. The substances involved in the reaction are the system and the engine, and the rest of the universe are the surroundings. The system loses energy by both heating and doing work on the surroundings, and its internal energy decreases. The engine is able to keep the car moving because this process is repeating many times per second while the engine is running. We will consider how to determine the amount of work involved in a chemical or physical change in the chapter on thermodynamics. As discussed, the relationship between internal energy, heat, and work can be represented as delta U equals Q plus W. Internal energy is an example of state function, or a state variable, whereas heat and work are not state functions. The value of a state function depends only on the state that a system is in, and not on how the state is reached. A quantity is not a state function. If a quantity is not a state function, then its value does depend on how the state is reached. An example of a state function is altitude or elevation. If you stand on the summit of Mount Kilimanjaro, you are at an altitude of 5,895 meters, and it does not matter whether you hiked there or parachuted there. The distance you traveled to the top of Kilimanjaro, however, is not a state function. You could climb to the summit by a direct route or by a more roundabout circuitous path. The distances traveled would differ. Distance is not a state function, but the elevation reached would be the same. Altitude is a state function. Chemists ordinarily use a property known as enthalpy to describe the thermodynamics of chemical and physical processes. Enthalpy is defined as the sum of a system's internal energy and the mathematical product of its pressure and volume. H equals U plus PV. Enthalpy is also a state function. Enthalpy values for a specific substance cannot be measured directly. Only enthalpy changes for a chemical or physical process can be determined. For processes that take place at constant pressure, a constant condition for many chemical and physical changes, the enthalpy change, delta H, is delta H equals delta U plus P delta V. Mathematical product V, P delta V represent work, namely expansion or pressure volume work, as noted. By their definitions, the arithmetic signs of V and W will always be opposite. Substituting this equation and the definition of internal energy into the enthalpy change equations yields delta H equals delta U plus P delta V, or the heat at constant pressure plus W minus W, which just equals the heat at constant pressure, where QP is the heated reaction under conditions of constant pressure. And so if a chemical or physical process is carried out at constant pressure with the only work done caused by expansion or contraction, then the heat flow QP and enthalpy change delta H for the process are equal. The heat given off when you operate a Bunsen burner is equal to the enthalpy change of the methane combustion reaction that takes place, since it occurs at essentially constant pressure in the atmosphere. On the other hand, the heat produced by a reaction measured in a bomb calorimeter is not equal to delta H because the closed constant volume metal container prevents the pressure from remaining constant. It may increase or decrease if the reaction yields increased or decreased amounts of gaseous species. Chemists usually perform experiments under normal atmospheric conditions at constant external pressure with Q equals delta H, which makes enthalpy the most convenient choice for determining heat changes for chemical reactions. The following conventions apply when using delta H. A negative value of an enthalpy change indicates an exothermic reaction. A positive value indicates an endothermic reaction. If the direction of the chemical equation is reversed, the arithmetic sign of its delta H is changed. A process that is endothermic in one direction is exothermic in the opposite. Chemists use a thermochemical equation to represent the changes in both matter and energy. In thermochemical equation, the enthalpy change of a reaction is shown as a delta H value following the equation for the reaction. This delta H value indicates the amount of heat associated with the reaction involved with the number of moles of reactants and products as shown in the chemical equation. For example, consider this equation. So that equation, the delta H equals negative 286 kilojoules. This equation indicates that 1 mole of hydrogen gas and half a mole of oxygen gas at some temperature and pressure change to 1 mole of liquid water at the same temperature and pressure, 286 kilojoules of heat are released to the surroundings. If the coefficients of the chemical equation are multiplied by some factor, the enthalpy change must be multiplied by that same factor. Delta H is an extensive property. No way. Okay. Sorry. Do it so that if they do 2 or a twofold increase or decrease, you should expect double or half the amount. The enthalpy change for a reaction depends on the physical states of the reactants and products. So these must be shown. For example, when 1 mole of hydrogen gas and half a mole of oxygen gas change to 1 mole of liquid water at the same temperature and pressure, 286 kilojoules of heat are released. If gaseous water forms, only 242 kilojoules of heat are released. Enthalpy changes are typically tabulated for reactions in which both the reactants and products are at the same conditions. A standard state is a commonly accepted set of conditions used as a reference point for the determination of properties under the different conditions. For chemists, the IUPAC standard state refers to materials under a pressure of 1 bar and solutions at 1 molar, and does not specify a temperature. Many thermochemical tables list values with a standard state of 1 molar, or atmosphere. Because the delta H of a reaction changes very little with such small changes in pressure, delta H values, except for the most precisely measured values, are essentially the same under both sets of standard conditions. We will include a superscripted O in the enthalpy change symbol to designate standard state. Since the usual, but not technically standard, temperature is 298.15 Kelvin. This temperature will be assumed unless some other temperature is specified. Thus, the symbol delta H is used with the degree symbol is used to indicate an enthalpy change for a process occurring under these conditions. The symbol delta H is used to indicate an enthalpy change for a reaction occurring under non-standard conditions. So standard conditions, I used to get mad. It's like, why is it standard? Because that's what they just chose. That's what they arbitrarily chose. And that's what we just accept. So the enthalpy changes for many types of chemical and physical processes are available in the reference literature, including those for combustion reactions, phase transitions, and formation reactions. As we discuss these quantities, it is important to pay attention to the extensive nature of enthalpy and enthalpy changes. Since the enthalpy change for a given reaction is proportional to the amounts of substances involved, it may be reported on that basis, i.e., as the delta H for specific amounts of reactants. However, we often find it more useful to divide one extensive property, delta H, by another amount of substance, and report a per amount intensive value of delta H, often normalized to a per mole basis. Note that this is similar to determining the intensive property specific heat from the extensive property heat capacity as seen previously. Standard enthalpy of combustion. Standard enthalpy of combustion is the enthalpy change when 1 mole of substance burns combines vigorously with oxygen under standard state conditions. It is sometimes called heat of combustion. For example, the enthalpy of combustion of ethanol, negative 1,366.8 kilojoules per mole, is the amount of heat produced when 1 mole of ethanol undergoes complete combustion at 25 degrees Celsius and 1 atmosphere of pressure, yielding products also at 25 degrees Celsius and 1 atmosphere. Enthalpies of combustion for many substances have been measured. A few of these are listed in Table 5.2. Many readily available substances with large enthalpies of combustion are used as fuels. Including hydrogen, carbon as coal or charcoal, and hydrocarbons, compounds containing only hydrogen and carbon, such as methane, propane, and the other major components of gasoline. Standard enthalpy of formation. A standard enthalpy of formation, delta H of formation degree, is an enthalpy change for a reaction in which exactly 1 mole of a pure substance is formed from free elements in their most stable states under standard state conditions. These values are especially useful for computing or predicting enthalpy changes for chemical reactions that are impractical or dangerous to carry out, or for processes for which it is difficult to make measurements. We have values for the appropriate standard enthalpies of formation. We can determine the enthalpy change for any reaction, which we will practice in the next section on Hess's law. Okay. The standard enthalpy of formation of CO2 gas is negative 393.5 kilojoules per mole. This is the enthalpy change for the exothermic reaction. There it is. There's the amount. Starting with the reactants at a pressure of 1 atmosphere and 25 degrees Celsius, with the carbon present as graphite, the most stable form of carbon under these conditions, and ending with 1 mole of CO2, also at 1 atmosphere and 25 degrees Celsius. For nitrogen dioxide, NO2 gas, delta HF is 33.2 kilojoules per mole. This is the enthalpy change for this reaction, and there it is. A reaction equation with half a mole of nitrogen and 1 mole of oxygen is correct in this case because the standard enthalpy of formation always refers to 1 mole of product, nitrogen dioxide. You will find a table of standard enthalpies of formation of many common substances in Appendix G. These values indicate that formation reactions range from highly exothermic, such as negative 2,984 kilojoules per mole for the formation of P4O10, to strongly endothermic, such as plus 226.7 for the formation of acetylene, C2H2. By definition, the standard enthalpy of formation of an element in its most stable form is equal to 0 under standard conditions, which is 1 atmosphere for gases and 1 molar for solutions. Hess's law. There are 2 ways to determine the amount of heat involved in a chemical change: measure it experimentally or calculate it from other experimentally determined enthalpy changes. Some reactions are difficult, if not impossible, to investigate and make accurate measurements for experimentally. And even when a reaction is not hard to perform or measure, it is convenient to be able to determine the heat involved in a reaction without having to perform an experiment. This type of calculation usually involves the use of Hess's law, which states if a process can be written as the sum of several stepwise processes, the enthalpy change of the total process equals the sum of the enthalpy changes of the various steps. Hess's law is valid because enthalpy is a state function. Enthalpy change depends only on where a chemical process starts and ends, but not on the path it takes from start to finish. For example, we can think of the reaction of carbon with oxygen to form carbon dioxide as occurring either directly or by two-step process. The direct process is written. Here it is. In the two-step process, first carbon monoxide is formed. Then carbon monoxide reacts further to form carbon dioxide. The equation describing the overall reaction is the sum of these 2 chemical changes. Because the carbon monoxide produced in step 1 is consumed in step 2, the net change is that one. According to Hess's law, the enthalpy change of the reaction will equal the sum of the enthalpy changes of the steps. There you go. It's just like a math equation. The result is shown in figure 524. We see that delta H is the overall reaction is the same whether it occurs in one step or two. This finding, overall delta H of the reaction equals sum of delta H values for reaction steps in overall reaction, is true in general for chemical and physical processes. Before we further practice using Hess's law, let us recall two important features of delta H. 1. Delta H is directly proportional to the quantities of reactants or products. For example, the enthalpy change for the reaction forming 1 mole of NO2 is plus 33.2 kilojoules. When 2 moles of NO2, twice as much, are formed, the delta H will be twice as large. In general, if we multiply or divide an equation by a number, then the enthalpy change should also be multiplied or divided by the same number. Delta H for reaction in one direction is equal in magnitude and opposite in sign to delta H for the reaction in the reverse direction. For example, given that, then the reverse reaction, the enthalpy change is also reversed. We can also use Hess's law to determine the enthalpy change of any reaction and if the corresponding enthalpies of formation of the reactants and products are available. The stepwise reactions we consider are 1. Decompositions of the reactants into their component elements, for which the enthalpy changes are proportional to the negative of the enthalpies of formation of the reactants, followed by 2. Recombinations of the elements to give the products, with the enthalpy changes proportional to the enthalpies of formation of the products. The standard enthalpy change of the overall reaction is therefore equal to 2. The sum of the standard enthalpies of formation of all the products plus the sum of the negatives of the standard enthalpies of formation of the reactants. This is usually rearranged slightly to be written as follows, with a sigma representing the sum of and n standing for the stoichiometric coefficients. Delta H reaction equals the sum of the stoichiometric coefficients of times the delta H formation of each product added together, so that's how you add it together, minus the sum of the reactants added together. The following example shows in detail why this equation is valid and how to use it to calculate the enthalpy change for a reaction of interest. All right, that's it. Sorry for the couple delays. This one's gonna be a little bit longer, but I think, I don't know if I mentioned it yet, but one of the things that I'm qualitatively measuring is the distraction factor as I do these. So when I'm not distracted, I can focus easily, and when I am distracted, then obviously my head goes in different places. But that's the thing. As I'm reading these things, I'm visualizing things and learning new things and stuff, and thinking of that butcher paper idea. Oh, dude, I'm so excited. It's going to be such a fun project.